Hi everyone, I'm Akash Yadav from University of Wisconsin Madison. I'm excited to present this collaborative work done with Dr. Pagilla from Texas A&M University and Dr. Anjana Mehta from University of Wisconsin Madison. In sectors like aerospace assembly and custom manufacturing, full automation isn't simply feasible. The layout change, the materials are custom, and the fixtures are asymmetrical, so robots and humans have to work side by side, sharing the physical load through co-lifting and co-manipulation tasks. In these settings, trust is everything. If a worker overtrusts their robot partner, they become more complacent. That's misuse. If they undertrust is, they intervene too often and disrupt the workflow. That's disuse. Calibrated trust is what enables safe and efficient collaboration. And here's the asymmetry that motivated this work. The robot doesn't get tired, but humans does. Workers fatigue over the course of a shift. So the question we asked is, what happens when trust and perceptions of the robot when the human partner becomes physically fatigued? Physical HRI or PHRI refers to any collocated interaction involving an exchange of haptic signals between a human and a robot. In these interactions, trust is shaped not just by the robot's reliability, but by the quality of coordination, the nature of physical engagement, and how well each partner pursues the other's intentions. Physical fatigue is multifaceted. It has both central component, where the nervous system struggles to maintain adequate motor commands, and peripheral components, where fatigue arises within the muscle fibers themselves. Both can impair motor performance. Critically, fatigue doesn't just affect muscles, it affects cognition, attention, and perception as well. Despite this, the effect of physical fatigue on trust and perception in physical HRI is largely understudied. We organized our investigations around three research questions. First, whether physical fatigue impacts trust and objective human robot collaboration performance. Second, whether fatigue changes how operators perceive the robot, specifically their perceptions of robot effort consistency, coordination quality, and transport quality. Third, whether those subjective perceptions actually align with the objective metrics. We used a collaborative UR10 robot arm with 6 degrees of freedom with 4 sensors on the joints. The task involved navigating a custom object through an asymmetrical object course with 3 designated checkpoints. A key design choice was the end effector. Instead of a rigid joint, we used a compliant hook design. This allowed the object to be naturally moved and rotated. For this study, we recruited a total of 40 healthy adults, 20 female and 20 male, with a mean age of about 25 years. The study used a 2x2 within subjects design, where fatigue condition crossed with phase, where the first 4 trials were the early phase and the last 4 trials were the late phase. Here's a quick look at the actual experiment. You can see the human participants and the robot arm collaboratively maneuvering the object through the obstacle course. Fatigue was induced using isotonic elbow flexion extension contractions with the 8-pound dumbbell performed to voluntary exhaustion. We verified fatigue induction using maximum voluntary isometric contractions measured before and after the exercise. A significant decline confirmed peripheral fatigue had occurred. Participants were not told the total number of trials. Each participant completed both conditions in the same session, first no fatigue and then fatigue. We collected both subjective and objective measures after each trial. On the subjective side, trust was measured with a single Sandpoint Likert item. Perceived exertion was captured with the Borg's RBE scale. We also developed 3 custom single item scales, one for effective coordination, one for robot's effort consistency, and one for transport quality. On the objective side, we captured position data from the robot's built-in encoders and from an HTC Vive tracker on the human end of the object. From those trajectories, we compared 3 metrics: dynamic time warping distance as a measure of trajectory dissimilarity between the two partners, acceleration as the second derivative of the position, and jerk as the third derivative, a well-established measure for movement smoothness in motor research. First, the ratings of perceived exertion confirmed successful fatigue induction. Participants reported significantly lower trust in the robot under the fatigue condition compared to the no fatigue condition. But the main effect wasn't uniform across time. There was a significant interaction between the fatigue and the phase. In the early phase, trust ratings were similar across the two conditions. But in the late phase, trust dropped substantially under fatigue, while it actually increased in the no fatigue condition. For effective coordination, H4 is partially supported with a striking crossover interaction. In the early phase, fatigued participants actually rated coordination as higher than no fatigued participants. Then, in later phase, this reversed. We interpret the early phase increase as compensatory mechanism, participants working harder to stay coordinated when they feel fatigued, but eventually that compensation runs out. For robot effort consistency, S3 is supported. Despite the robot performing identically across both conditions, participants rated its effort as significantly less consistent under fatigue, but again only in the late phase. For transport quality, H5 was not supported. Participants actually rated transport quality higher under fatigue in the early phase, even though the objective performance metrics were identical. Turning to the objective metrics, S2 was not supported. Physical fatigue had no effect on D2W distance and acceleration or jerk. The robot's performance was identical across conditions, and the human's trajectory quality was also maintained. The only significant effect we observed was a phase effect on DTW. The trajectories became more similar over time, suggesting participants learned to coordinate with the robot regardless of the fatigue stage. For RQ3, the picture was mixed. There was a statistically significant but weak negative correlation between DTW distance and perceived effective coordination. S7 was not supported. Neither acceleration nor jerk correlated significantly with perceived non-sport quality. This is a real challenge for evaluating HRC system. Task performance metrics alone are not enough. We have a few key takeaways. First, physical fatigue reduces trust, but the effect accumulates over time rather than appearing immediately. Initial cognitive compensation masks the fatigue effect early on, but resource depletion eventually leads to trust decline in the late phase. For real-world system, this argues for real-time fatigue monitoring using variables, force sensors, or computer vision. Second, fatigue distorts how operators perceive their robot partner. Effort consistency was rated lower, and coordination ratings were crossed over, even though robot did exactly the same thing in both conditions. The negativity bias induced by fatigue is a real phenomenon that system designers need to account for. Third, perhaps the most fundamentally, the subjective and the objective measures are dissociated. The transport quality was rated higher under fatigue, yet the kinematics were unchanged. Coordination perceptions were only weakly linked to trajectory similarity. This tells us that PHRI evaluation needs to go beyond task metrics. We need approaches that are resilient to the cognitive state of the operator. On the implication side, this work argues for cobots that monitor operator fatigue in real time through EMG, force sensors, or computer vision, and adapt their motion profiles accordingly, reducing speed or jerk to communicate reliability. It also reinforces that evaluating HRC quality requires both subjective and objective measures together. There are several limitations in this work. The trust was measured using a single item. Our sample was healthy college students rather than industrial workers. The task was short, and we didn't counterbalance for condition order. Looking ahead, we want to extend this to diverse populations, more complex environments, and study explicit leader-follower dynamics. Neural measures like EEG and FNIRS can also enhance the understanding of cognitive mechanisms behind these perceptual shifts. This work was supported by NSF. Thank you for watching and enjoy the rest of your HRI conference.